what do we have in the integral sign? Definite integrals. What do we got? Found. This entire chapter is going to be definite integrals applied, meaning we're actually solving for numbers, meaning we're actually solving for expressions, maybe gross ones, that give us some sort of geometric measurement. In 6.1, what is that geometric measurement we're looking for? Area. In 6.2 and 6.3, it's going to be volume. We're going to be searching for geometric dimensions, geometric measurements that are basically impossible to solve, usually impossible to solve with the normal, like, hey, the area of a rectangle, the area of a square, the area of a triangle, because is this any of those normal, original, elementary geometric shapes? Nope, it's like a flower petal. Well, that flower petal needs to be defined by a curve above, needs to be defined by a curve below, and then if we use integration, we can find that exact area. We're going to be finding volumes of vases. We're going to be finding volumes of rain droplets. We're going to be finding volumes of weird, like, funneling things, or donuts, or, well, those are technically called toruses. But anyway, we're going to be finding volumes of crazy shapes that basically, with these areas and then with the volumes, all we need mathematically is some sort of definition of the bound, the boundary, the side. Now, this one yesterday, for those of you guys that were here, remember I'm talking to period 6, not just period 1. We were able to say, like, hey, this could be bounded by the y-axis. And so they could put, like, a 0 in an interval if they were defining it for you, if there was no clear, like, natural intersection point bounding it. This one had 2 clear intersection points. They could have said the x-axis. I actually totally ignored the picture, so in period 6, I actually saw there's an A and there's a B. I'm supposed to use that. Oh, well. But I did go ahead and say, what if that B was here, or here, be the intersection point, or here? Oh, no! Orange was on top, green was on bottom, but now green is on top and orange is on bottom. Why did we put the square root first in the subtraction and the x squared second? Why did we put the orange first, although you can't see it so well, I didn't color coordinate, sorry. And then we put the G second. Why was that okay for most of this picture to put the top curve and then the bottom curve?
Because of the x.
Okay, positive. What are we trying to keep positive?
Like the area.
Okay, if we're doing geometric, we are thinking like in practical geometry terms. Practical geometry terms, area is always positive. So we're not talking about displacement to the right, to the left. That could be positive, negative. We're not talking about area applied. We're literally talking about area. So if we want area to be positive, we need the bigger minus the smaller. That's obvious, right? But what's the problem if something changes, like the green is now on top and the orange is now on bottom?
Slap some absolute value bars.
Slap some absolute value bars being like, uh-oh, things can change. And if uh-oh, things can change, what do the absolute values tell us to do if uh-oh, things can change? And this is in your forever card number 43. Here we go. What's my little warning?
Of integral intersection between them.
We have to be ready for, life lesson. We have to be ready for whatever may come. Meaning, if there is an intersection, if everything gets flipped upside down, we have to be ready for it. Now, ready for it in math, it's like, okay, absolute value. Although some of you forget how to do absolute value. And so, yeah, it's there in order to protect you, but if you don't know how to use it, well, that's not going to be very helpful. Oh my goodness. Let's keep going. Stop. Let's just stay in math. So, forever number 43 is warning us, absolute value, everything can change. Now, kiddos, in this one, though, do I have to split up between 0 and 4? Is there any reason to? If we know the picture, if we can look at it. Any reason to split up?
No.
No, because there's no change in orientation, right? We could do the top minus the bottom. Why is there a dot, dot, dot at the end? You're going to have to solve a definite integral. Now, quick reminder, just in general, how do we solve a definite integral? What's the first thing you do? AKA anti-derived. Some people just forget that integrate means anti-derived. So wouldn't we have to make this x to the 1/2 power and then 2/3 x to the 3/2? Just a quick reminder for those of you guys, we are not going to do this all chapter long because we don't have time and you've already learned how to do integration. But do you need to remember it for these problems? Yes. What would you do next?
Plug in.
What are you not going to like plugging in if you have to do a multiple choice match to a single number? I can't just box things.
Easy.
The fractions are easy. Why are the fractions easy?
The 0. Or
Okay, well the 0 is going to be easy. Yeah, great. Mine is 0, but what's not going to be so easy?
Missing 1 4. Oh, no, time. Sorry. I saw the time.
0 plus 0?
Yeah.
Right?
Sorry.
No. I wanted you to make sure, like, I am doing the full thing. But what's not going to be so easy?
Plugging in 4 from this. Yeah.
Come on, stare at it, right? You guys don't like it, let's admit it. But what is 3/2? Isn't it the same thing as?
4 square rooted.
Well, that's one way, but isn't that another way? The same way we go from powers to fractions, we can go from fractions to go from radicals to fractions, we go from fractions to radicals. What is 3/2?
Cube.
Okay, cube, square rooted, but no. Come on, use your math to help you out. Isn't
Square root
3/2 the
4.
same thing as 1 1/2?
Yes.
Right? So this 1 1/2, isn't it 4 to the 1 times 4 to the 1/2? Do you see it?
Wow.
Isn't that so much easier on your brain rather than the square root of 4 cubed? I'd have to do 4 times 4 times 4 is 64, square rooted is 8. Okay, that one's not bad. But what if it was something like 16 to the 3/2? 16 cubed, right? Like, so much easier. 1 1/2, you see it?
Does that work for every number? Like 16 over 3?
Yeah.
Okay.
Yeah. Which technically would have made teaching Algebra 1 so much easier if you guys were so much better at fractions way back then. And I'm thinking, not you guys, I didn't teach you, I taught Justin and all them, but I'm thinking my Algebra 1 class right now, because to be honest, I did it the same way that Algebra 1 teachers have done it forever, because frankly, they're just awful at fractions. But anyway, because if you were to have something like the square root of 242 x to the 9th, like mathematically, it's so much easier to think of this as x to the 9/2, and 9/2 is just 4 1/2. So much easier. But the problem is, way back when in Algebra 1, that was just too complicated for your brains, for most of your brains to take in. But it's so much easier if you think about this as just being a 1/2 power. Raise a power to a power, you multiply, change that to a mixed number. You always know what the simplified form is. But in Algebra 1, it's too much for a lot of Algebra 1 kids. Which is sad, because then you just kind of like, oh, I have to have these groups, and it's cubed under a square root, and that's good, but 1 1/2 is so much easier. Anyway, sorry, did I prove my point? I should be quiet. We have 1/8, 4 squared. It's fun. It's fun that I can teach algebra to my calculus kids, which I do all year long. Factoring. Okay. So, anyway, do you guys see how you could make it a nice, easy number?
Yes.
Okay. Can I just put a dot now? What was different in number 2? We didn't fully get into this one, and this is technically the right minus left dy example in your forever card. This has a picture. Makes life a little bit nicer. I just had all that work kind of crash into it. It's a little bit sad. Why did I do f first, minus g second, and why the heck is this in terms of y? What's different about the one, or from the one that was right up above?
Well, now it's like you're doing like vertical down.
Such a weird graph.
Yeah, it is a weird graph. It's weird because, isn't this like a failure of a function? But come on, in real life, is everything functions? No, we have like circles. They fail, and they're like one of the most basic elementary shapes. So come on, it's not a big deal. We can have non-functions. All those implicit guys were maybe non-functions that couldn't be written as y equals f of x without a plus or minus, which is really 2 and 1. Anyway, we could go solving for y, but we would have a function here, we have a function there, we have a function there, and we have to put all of that somehow in an integral bleh. Or we could leave it in terms of y with a dy, and we could say, instead of thinking top minus bottom, let's think what's on the right versus what's on the left.
Is that the right or this is the right?
What we're technically doing is, instead of having rectangles going up with a base of dx, what we're doing now is we're having rectangles go to the right with a base of dy. It's basically the exact same thing as we were doing, just now it's with dy's instead of, wait, every time we were doing dy's, we were doing this sideways thing? Yep. We were just looking at it a different direction.
And I skewed.
We were just looking at a different direction. So if we go to this guy, then we're going this way. If we minus and go to this guy, we're going this way. And hey, minus and negative ends up being a positive, so we end up getting that area and putting it all together. But just like up above, orientation could switch, so we have to be careful. Now, kiddos, here's a dilemma. This one, I didn't label the numbers, so you don't know where they hit. So if the graph doesn't have labels as far as the intersections, what are you going to have to do to figure out your bounds?
Find where they equal each other.
Ah, and that's the joy of natural bounds. If intersections are involved, we can find them ourselves and say, okay, 2 minus y squared is equal to negative y. Set them equal to each other and go find the y's where they intersect. Now, up above, I don't think it was in this class, and I think it was actually on the page before. When we talked about natural bounds, I said it, I'm just not sure if we wrote it. I'm putting it in green because, oh my goodness, we've learned this a million times now. Factoring is the key to getting all the intersections. So move that y, don't move that y. Move that step to the other side, right? Y squared minus y plus, minus 2. Are we going to end up with y minus 2 times y plus 1? You guys gotten guessing checked down? Or do you still make the x? Just do what works.
We asked our bounds.
Huh?
So bounds, right?
Well, almost our bounds. Don't we need the zeros of those, right?
Yeah.
So then y is equal to? 2. So this guy is negative 1. This guy is 2. In this weird case, I'm not using both of them because look at the shading. What are my bounds actually going to be?
2 and 0.
We're putting in order 0 and 2.
Yeah,
Right?
sorry. Throwing it out there.
But yeah, you're right as far as the number values. Mathematically, it'd be a little dangerous because we would have gotten negative 1 and 2. Remember, they're y's, not x's. But yeah, I heard a wait.
Never mind. I thought that the intersection of 0, but that was the one line. It wasn't.
Yeah, that was just the, hey, x,
Why?
y equals 0. What's that end? Y equals 0 is that boundary. I'm not going to leave that. That's gross. All right. Beep, beep. If you can make it pretty, why not? I've got a beauty. All right. So then we would go ahead and throw this in. I'm going to do a ... in just a second, but putting this dude in his proper space. Why am I doing parentheses around the 2 minus y squared, even though in this example it will not make a difference? And see that I'm putting in the whole function, and if the order was switched, wouldn't it be crucial to have those parentheses?
Yeah.
To distribute that negative, to get your proper integral, and then you would solve. Kathleen?
Why did you use 0?
The picture was given to me, and the shading in the picture was only from 0. They would have, in words, they would have done something like this is an area bounded by. Actually, this is probably really helpful for you guys to see. If they had not given you a picture, which they definitely didn't have to in this one, bounded by the x-axis, x equals 2 minus y squared, and x equals negative y. Ooh. Oh, I'm not sure if they could have just done that.
I think it's just that.
For y. They would have to tell you what direction. That's why they probably wouldn't give you this graph. Because if they just said 0 in the curve, it could have been the lower or it could have been the higher. But if they say the x-axis, that means it has to be some sort of boundary to an area. Yeah, Adam.
If we just have like the words, just like, because we have to pick the right order, would it just be better to just do like absolute values then?
And you're going to be looking for intersections anyway because they didn't tell you the bounds. Right? Yeah, so then you'll know the intersections, you'll know whether or not to split up. The tricky part is when they put an axis in, because the axes, most of you don't think of it as, oh, wait a minute, that has an equation also. And some of you might think that this should be going in here when it's not. Axes are almost always giving us something as far as the bounds. Captain? Well, the graph, technically I put those little dashes in yesterday. The graph didn't have any labels whatsoever. So you wouldn't have known what they are unless you went and said, like, I need the intersection in order to know how high to go. Because this shading, what was it bounded by? Green, blue, axis, point. So what did I do? You're 0. Let's find you. I know you and you. You're in terms of y. Awesome, because right minus left totally works for the entire region. Does that make sense? Now, if for any reason, just to show you guys a quick little what could have happened, like why not? How bad could it have gotten? That's not always safe in life, but anyway. Okay, so what if this had kept going? Usually I'm just impatient. That's not safe. Okay. What if it had kept going to here and here? Okay.
Hourglass.
What if I had kept going? Hourglass if you spun it. Guess what's coming?
Not again.
So fun, my artistic ones. It's so fun. Man, those surfaces
Oh,
of revolution.
no.
Ah! Okay, they're coming back. Anyway. Discs and washers. Alright, come back. What if it had kept going? Is the blue always on the right?
No.
Ah! I would have had to split it up because now the green's on the right and the blue's on the left. And so when I subtract, that's going to be negative, and that's not geometry. Where would I have split it up? I would have gone from -1 to 2, and then they would have had to tell me when to stop, because otherwise what would keep happening?
Yeah. Area.
So they would have to have told me where to stop or shaded where to stop. But that's a case, Kathleen, where we still would have had to split up. So the possibility still exists that we have to split up. Now, I'm just making this one silly, simple problem into a hard problem. I am so sorry. That's a good example.
Oh boy.
These ones you don't have pictures, which is kind of helpful. Let me just see where we go. And then we have FR cubes. Okay, so let's go ahead and do this one, because I'm pretty sure your book has one where they want you to solve it 2 different ways. I'm pretty sure the book has one, because I'm trying to make it applicable to your homework help. Why don't you guys go ahead and let me zoom in so you can get the basics of this down. The way this is given to you, y squared equals 4x and y equals 2x minus 4. The way this is given to you, what does your brain naturally think? Dx or dy? Just real quick. Dx. Because you're like, there's x's everywhere. But Kyle, you're like, but wait. Why are we stressing about that FRQ? Come back. But wait. Oh, okay. But wait. Kyle said there was a y squared. So even though you think dx, what actually is probably easier? dy.
So do we have to solve 4x?
Now, what do you see down here that you're going to be doing anyway? One is dx and one is dy. So keep it like this to start. But then when we come down here, you're going to have to actually get y as a function of x, aka get that guy by himself, aka you're going to have a positive square root and a negative square root and your other guy.
Oh,
But this one, well, maybe you only need 2 to get x by itself. If I were you to set up this problem, start with what they give you, but then realize, hey, I can go 2 different routes. It looks dx, but if it was, I would have to do a plus or minus square root of that guy, and then combine it with that guy. This one, I might just need 2. I'm going to go ahead and color code them down here just so you guys can see what's going on. We'll go ahead and make those our blue, and we'll go ahead and make these our green. So get for me y by itself, get for me x by itself, just to go ahead and start defining our curves that we're going to be using. If you want to be super snazzy, we definitely need those intersection points because, Kathleen, they're not given. Yeah? So intersection points, you got to set something equal to itself.
Wait.
Or to another.
What is WR?
With respect to.
Oh, these are
Work.
too many very
I know.
With respect to. Remember ST, such that? WRT, with respect to? No?
No.
Yeah. Yeah. Mm-hmm. Mm-hmm. Because it's geometry. Remember geometry, if I want the area, I need this positive plus this positive. Does that make sense? Like if you're doing the area of a house, you need the bottom rectangle, you need the top triangle. And maybe the yeah.
So what if I need bounds? It's going to be square root of 4x equals 2x minus 4, right?
Well, that's one way.
If I square both
Or
sides,
could you
that's
just
equal?
set those equal to each other? That might be easy. Because in this one, isn't the positive square root going to equal somewhere? And isn't the negative square root going to equal somewhere else? Adam's being positive. Thanks, Didn't even mean for it to be funny. Thanks, Sean.
Like Adam.
Although he's laughing like it was a dad joke, which my dad has some winners. I'm not that bad, I promise.
John, you've been funny the last few days. Like yesterday. Took a break.
Could you guys take the square root of 4 and make it 2? Sure. Do we need to? It's up to you. Then we have 2x minus 4. If I was to label stuff, this would be my y1, this would be my y2, this would be my y3. Because y1 is the positive square root. Functions have to pass the vertical line test. This would have to be the negative square root. What's in terms of one function, or what's in terms of y can be 1, whereas what's in terms of x has to be 2. But then over here, this guy, wouldn't this just be y squared over 2? No, over 4? Wouldn't this just be y plus 4 over 2? Oh, that's nice. There's just 2 of them. Either way, you have to set them equal to each other. I think I'm going to set the y's equal to each other because that looks easier. And I'm trying to look for my intersections, yeah? So y squared all over 4 equals y plus 4 all over 2. I'm going to cross multiply. Some of you tried doing that in a very awful way.
What are you talking about?
Cross multiplying works. I'm going to do it the old-fashioned way.
Miss D, I have a question.
I
Two.
might have an answer. Huh?
If I multiply 2 on both sides, why would it be?
If you multiply by 2 on both sides, you get rid of the 2 and you almost get rid of the 4, right? That's supposed to be this way. So you can multiply 4 up on that side and multiply 2 up on that side. It's technically what cross multiplication is, just a trick to simplify life. Ooh, I can divide everything by 2. And move that over here. So dividing everything by 2, moving that over here, I end up with minus 2y plus 8. Oops, minus 8 equals 0. Minus 8, I believe 2 and 4 is going to go quite nicely.
Very nicely, actually.
Just which order? Minus 4 plus 2, thinking about that sign at the inside, I end up with y is equal to negative 2 and 4. Do you see how calculus tries to keep the factoring fairly easy for you? Sometimes. So we end up with knowing these intersection points and saying, hey, this one's going to have a y of 4 and this one's going to have a y of negative 2. How do I know that? Well, he's higher and he's lower. Okay. But those are y's. What else do I need? X's.
So we can plug in the y to the x on x.
Plug it in, 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 plug it in. I don't know. There's so many different equations. Plug it in. Just be careful on the square roots. One's going to give you a positive, one's going to give you a negative.
Let's do y plus 2 x minus 4.
Wait, I'm confused. Why wouldn't we be plugging into the x one if we have the y?
We can't plug. Oh, well, we can. I was just saying, I mean, there are lots of y's.
Oh,
we
like
can,
solving.
we can plug in lots of places. But yeah, if we plug in here. Did I write that squared weird? No wonder it looks so funny. Or why put it as a subscript or a superscript? There we go.
Just look at the top.
Okay, sorry, coming back. If we plug in negative 2 plus 4 is 2, 2 over 2 is 1. That's 1. And then if we plug in 4, 4 plus 4 is 8, 8 over 2 is
1. Oh, 4. 2.
2. I almost did 4 too. 8 over 2 is 4.
It's 4.
Yeah, which is definitely
Well, I was right. Why did I think it was 2? Oh, 8 over 4 was what I said.
Yeah, you said 8. Didn't you say 8 over 4?
Yeah, I think I said it wrong. 8 over 2 is 4. Right? 8 over 2 is 4.
Oh,
I said it wrong. 8 over, yeah.
Oh,
Okay. Whew. So that was just the setup.
and now we have to do
Well, plus it's doubly as hard because, I mean, one's with respect to y and one's with respect to x. So if we were trying to find our area, one way is going between negative 2 and 4 from a y bound to a y bound, asking yourself what is on the right and what is on the, come on, we've been distracted enough, give me my last minute and a half.
Sorry.
What's on the right, what's on the left? I have green, which is my x2, which is y plus 4 all over 2 minus, would you guys put your brackets and have your proper notation and not let them steal any of the points? Minus y squared over 4. What's on the right, what's on the left? Ha, got it. But if I was doing it in terms of dx, if I was doing it in terms of dx, would you guys realize that I would have to go from 0 to that nasty 1, and then I'd have to add from 1 to that 4. Why would I need 2? Well, my orientation switches. I do have the blue on top of the green for the majority of the time, the top blue being the 4 square root of 4x blue. But I actually only have that happening from 1 to 4. Minus. Why do I only have it happening from there to there? Just check it. What's on top? What's on bottom? Moving, 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 but what's on top and what's on bottom for this little portion? I have the positive square root minus the negative square root for just a little itty bitty bit right before that intersection. Oh my goodness, which one looks easier to solve? But guess what, both of them are going to end up equal. The same thing. Kiddos, technically homework is due tomorrow, but it's not turned into Google Classroom. I'm changing that to Monday. You guys are going to try to get as far as you can and tell me where you got stuck. My guess is you'll get stuck somewhere where there are words.
Most likely.
Okay, you better start tonight. I might do a spot check to see if you started, but it will not be the full submission on Google Classroom. I will change that to Monday. Bye, cool kids. I'll see you later. Love you all. Stay safe out there. Don't sneeze on people. Wash your hands. We'll do what we can.